Leave
All
a
right.
meeting.
Yes. Welcome, everyone. For today's kind of seminar, we're happy to have Brian Swingle. Brian has done pioneering work in tensor networks, entanglement, and holography. And he's thought a lot recently also about quantum chaos. And today he'll tell us about hydrodynamics and the spectral form factor.
All right. Thanks a lot for the invitation and for coming out. Hope you're all doing well. Sorry I can't be there in person, but hopefully again soon. Last time I was there, actually, I got to meet Leo and share a drink with him as well as his way. And we talked about normalization and tensor networks. It was a lot of fun, and hope that can be that way again sometime. And yeah, today I want to tell you some interrelated tales about quantum chaos, specifically about the properties of energy eigenvalues in a quantum chaotic system and how that connects to hydrodynamics. At least that's one of the main themes. And I've been thinking a lot about quantum chaos from different points of view in the last couple of years. And this is a somewhat different direction that we're starting to think about now. So I'm very happy to hear your feedback afterwards. And of course, if you have questions, don't hesitate to stop me during the talk. And I'll just also acknowledge, this work has been supported by a number of groups listed there below. We're grateful for that support. So yeah, so this is really about quantum chaos. That's the broad subject that I have on my mind. Of course, to start out, we should remind ourselves what classical chaos is. That's actually a very complicated and interesting topic. Probably the thing you most think of when thinking about classical chaos is the butterfly effect. This idea that small changes lead to big effects down the road, or that, more precisely, that small deviations in phase space grow exponentially at early time. And there's been a lot of work trying to generalize this to the quantum setting. I think a really nice way to think about chaos is in terms of this idea of deterministic randomness. So the past predicts the future, but the approximate past does not predict the approximate future. So, even the smallest amount of ignorance kind of gets amplified. And there's been a long history of asking how to generalize these notions, or do they generalize, and how they generalize to the quantum world. One point of view pioneered by Barry, I think, some years ago. I don't know if he still adheres to this, but this was at some point a point of view that he advocated, was that it's not really quantum chaos, but quantum chaology, which is like the study of the quantum signatures of systems that would be classically chaotic when you unquantize them. That's, of course, a little funny because not every system has a nice classical limit that you can think about. But anyways, it made a lot of useful progress possible. One interesting wrinkle in that comes from this interesting recent work of Rosenbaum, Bunamovich, and Glutsky, where they pointed out that there are quantum chaotic systems, that is, systems that would be quantum chaotic according to some definition I'll give in a little bit, which, when you take the semi-classical limit, are actually classically non-chaotic. They're regular. So it's an interesting interface between these two worlds, and I don't claim that there's any completely general understanding at this point. So then what is quantum chaos? This is also still a heavily debated or discussed subject. I still like the idea that it's sort of deterministic now quantum randomness. And you may say, okay, quantum is already random. What do you mean? But that's sort of, any pure quantum state is deterministic in the right basis. But there's a certain sense in which this kind of determinism is not possible when you have quantum chaos, at least for subsystems, for example, or for certain kinds of nice observables. So there is a precise sense in which these quantum chaotic systems are very quantum random, but in a deterministic way. And under this general umbrella, there's lots of different sort of manifestations of quantum chaos. So one very popular manifestation is what I call sensitivity. So think here echo type experiments, where you kind of go forward and backwards in time and compare the result. This is probably the most direct analog of like the classical butterfly effect. You could think about out-of-time autocorrelator sitting in this box here. Then there's this direct idea of randomness. So looking at properties of the Hamiltonian and seeing to what extent they have some randomness in their character. So for example, the idea that energy eigenstates are effectively random. This is the eigenstate thermalization hypothesis in some form. or more specifically for the purposes of this talk, the idea that the energy levels are random matrix-like when you have chaos. So Barry and Tabor pointed out that when you have an integrable system that you quantize, you expect Poisson level spacings. And then Bohigas, Johnny, and Schmidt said, well, if it's quantum chaotic, then you should get something more like Wigner-Dyson. This was, of course, one of, in some, I don't think he used the word chaos, but one of Wigner's motivations for thinking about nuclei in terms of random matrices. So they're sort of very complicated and you have all kind of possible transitions. So it should be some generic object like a random matrix. So this is one of the main subjects we're going to talk about today, the idea that energy levels of a quantum chaotic system should be random matrix-like. Another manifestation of chaos is complexity. So something I've also worked a lot on is the growth of circuit complexity. That is the difficulty of preparing a given state as a function of time evolution. You can also ask about the complexity of eigenstates. And then maybe the most visible manifestation of chaos is something that we're most familiar with from experiments, which is thermalization. The idea that if you take some quantum system, even if it's in isolation, if it's sufficiently chaotic, then when you ping it, it will approach equilibrium and forget that ping. So it loses memory of its initial condition effectively, although the ultimate underlying dynamics is unitary. And this is, of course, closely tied to transport phenomena and hydrodynamics. And this is going to be the other kind of key theme of the talk, is connecting energy level statistics to hydrodynamics. So we'd like, for example, to characterize to what extent all of these different things co-occur in a given system, what are the relationships between them, and so forth. And yeah, so today I'm going to focus on these energy level properties and on hydrodynamics. Now, why now? There is as you may know, a very old and storied literature that goes back decades on quantum chaos. It mostly stuck to a single particle context. So sort of thinking through things again in a mini body context is certainly interesting, but I think there's a lot more good reasons right now to think about quantum chaos. One of the most prominent is just the possibility of new experiments. So given all these attempts to create quantum computers and to probe quantum coherent systems at long times, we have increasingly the ability to take a quantum system, to effectively isolate it, and to watch its dynamics over a relatively long time period. So you can really see coherent quantum many-body effects. And because far from equilibrium is sort of natural, it's easy to prepare a simple state rather than to prepare like a ground state or a thermal state of some complicated Hamiltonian. Easy to prepare a high energy excited state that's simple, like a product state. These far from equilibrium experiments are natural, and in many cases, they more or less directly probe chaos. They certainly probe thermalization and equilibration. Now, another good reason is sort of the theory counterpart to some of these experiments is that we have this influx of new ideas from quantum information that are giving us a lot of new tools and new ways of thinking about quantum chaos in terms of like information spreading, information hiding, error correcting codes, and so forth. There's also a strong motivation from quantum gravity because we expect that black holes are highly chaotic. In fact, in a certain sense, they're maximally chaotic in Einstein gravity. And this chaos is closely tied to a number of interesting problems, most notably the black hole information problem. And then actually one of my original motivations, because my background is actually strong correlation electron physics, was thinking about transport physics, the transport of heat and charge in strongly interacting materials, for which we don't really have any kind of general framework for computing those properties. When you have weakly coupled system, maybe you have a Boltzmann description or something like that, and we know it at long times and long distances, you have a hydrodynamic description. But if you want to actually calculate those transport coefficients, that's a problem that really involves the microscopic physics, and we don't have a general way of doing that. Now, maybe that's too much to ask for, but we can still hope that a deeper understanding of quantum chaos will help us better understand and compute these kinds of transport properties. And indeed, that's paid off in some sense that I won't talk about today, but I'm happy to discuss afterwards. So I think it's a good time to look. And so what are we going to talk about today? We're going to talk about chaos in the spectrum. And I'm really going to talk about two papers, one which appeared with Mike Weiner and Shaokai Jian, which is about a kind of a measure of chaos in a sort of hybrid system where the single particle levels are chaotic, but the many body levels are non-interacting. So you take chaotic single particle levels and you stack them together, like these are going to be fermions. And you're going to see some interesting behavior there. And then that's kind of a special case that's representative of the integrable limit of this story, where you have non-chaotic dynamics. And then at the other extreme, you have some kind of strong chaos. So I'll review that. And then I'll talk about upcoming work with Mike about how we can kind of connect weak chaos with strong chaos. That is specifically how we can go from a system where there are many approximately conserved quantities and see at long times the emergence of random matrix-like spectral properties. And the quantity I'm going to think about is called the spectral form factor. I'll discuss it in much more detail below, but this is the basic idea. You have time evolution operator U, which is just the exponential of the Hamiltonian. And you're taking the trace of this thing. So it's like a return amplitude. You start in some state, you evolve for a while, and you ask what's the amplitude to come back to that state. Then you square that, or you sum over all amplitudes, and you square it, and you take a disorder average. And I'm not going to be super explicit about what this disorder average is. It could even just be averaging over time, in fact. You average over the amount of time t that you evolve for. But anyways, you do some kind of disorder averaging. And I'll discuss this a little more later. And this is the spectral form factor. So in terms of pictures, you have sort of two contours. A contour that goes forward and is identified, you identify these two blue dots, and a contour that goes backwards and you identify the red dots. And the basic signature of quantum chaos is that at intermediate times, which I'll define, but sort of after the fast stuff has happened, but before very long times, you're going to find that this spectral form factor is just linear in time. And so understanding this is going to be one of the main points of the talk. And just to emphasize again, there is really a wide spectrum of possible behaviors. So for integrable systems, I'm going to show you one example, but they're a rather heterogeneous bunch. You know, it's not just all Poisson statistics, for example. You can get quite a variety of different behaviors. But at the other extreme, chaotic systems, at least at long time, are supposed to really have this random matrix-like energy levels. And in fact, this is so universal that it's one definition that widely circulates of quantum chaos. We just define quantum chaos to be a system that displays, or an ensemble of Hamiltonians that display random matrix-like level spacings at late time. Meaning, for example, that this spectral form factor is linear in time after a sufficiently long time. And then from the definition, we could hope to prove other things like that thermalization happens or whatever. But of course, in the generic case, you're going to be somewhere in between. You know, maybe you have nearly conserved quantities, like you have quasi-particles that have a very slow scattering rate, or at the very least, you have a diffusing energy mode, which will have very slow dynamics. And so we want to understand kind of how to go from the integrable extreme to the chaotic extreme as a function of time. And that's what I'm going to talk about today, sort of surveying some recent developments and presenting a theory of this crossover to late time pure random matrix theory. So I'll just pause here and ask if there's any questions before I go on to the first topic. All right. Yeah, let me also just mention that, you know, there's a lot of prior work here. This is not going to feature very directly in the talk, but just so you're kind of aware of it. Like the first place where I know of where this connection between transport and random matrix properties showed up is in this famous paper of Altshuler and Schlossky in '86, where they basically looked at the number of energy levels in a certain energy window and showed that it looked random matrix-like once you were past a time called the Thouless time, which was set by the diffusion constant of the system. It's basically the time it takes for you know, some localized blob of charge to diffuse over the whole system. After that time, you found random matrix-like behavior in this number of energy levels in an energy window. And before that time, the variance was different. Okay, so this was an explicit connection between the so-called Thouless time, which was really defined from mesoscopic transport with these random matrix properties. But now that notion of Thouless time, which I'll define more precisely shortly, has really kind of, in many contexts, just come to denote the time beyond which things look sort of generic or random matrix-like. So that's just one blip out of a very large literature, just to give you a sense of where things stood. This was known already in the 80s, but for a single particle system. Then more recently, there's been a lot of analytical results in many body models of interest. So for example, Bertini, Coase, and Prozin showed how to get the spectral form factor exactly for a certain kicked Ising model. This is an Ising model that's driven, so you periodically kick it. So it doesn't conserve energy and has in fact no conserved quantities, or yeah. So it's sort of maximally simple from a certain point of view. And then Saad, Shankar, Stanford showed how to get this ramp in SYK. And there's been a lot of other work that I won't really discuss here, but it's nice to be aware of. The particular question of the onset of random matrix theory in the many-body context has been studied recently in quite a few different works. One from the group of Leah Santos, where they looked at sort of return probabilities for initial states. And then Gerbian and that company and Friedman and company looked specifically at the spectral form factor, asking kind of the time scale for the onset of this pure random matrix behavior. And I'll come back to these papers a little bit later. And then, the tool that we're going to use towards the end of the talk is this theory of fluctuating hydrodynamics. And so here I just listed some of the key papers in that subject. In particular, we're going to think a lot about, I'll use as an example, the theory of energy diffusion discussed recently in this paper of Luca and friends. Okay, so you'll see that later on. So let me start out with this model, just to give you a sense of the integrable end of things and one concrete thing to hang your hat on, and also a nice way of introducing some of the techniques with a fun result at the end. Okay, so here's the model. This is the SYK model, Sachdev-Kitaev model. You have a bunch of fermions, Majorana fermions, n of them, and they have some Q-body interaction. And all the coefficients are random Gaussian variables fixed in time, but you get the Hamiltonian, by choosing a particular set of these couplings. And most attention has been paid to the case of Q equals 4, which is an interesting quantum chaotic system. I want to talk about the case Q equals 2. This is like single particle physics, but in a many-body setting where the single particle levels are chaotic. Literally, they're just given by the eigenvalues of this random Gaussian random matrix. Okay, so I'm just studying the problem of single particle levels are chaotic, like you have some potential, your particles in a billiard or something, and they have weak interactions, so we idealize them as having no interactions, and we want to know what the spectral form factor is in this case. The reason why I was interested in this problem is because, as I said, a lot of the older quantum chaos literature thinks with a single particle problem, so we wanted to understand a little bit how to connect the single particle setting to the many particle setting, and that's one of the reasons why we thought about this. But it's interesting just as an example of this machinery. And so we're going to compute this quantity, G of t, which is the spectral form factor. Here, Z is now just another name for this trace of U. It's the partition function at imaginary temperature or real time. And then I'm going to normalize it in some way. And here is a picture of what we're going to get. So this blue curve is from numerics, where we just literally diagonalize this and compute the spectral form factor using the formula I gave. And then the red curve is our theory. Okay, and the theory only works out to some fixed time. At times of order n, it breaks down. But in principle, it should be good up to any finite time. And you'll see that there are certain characteristic regions. Basically, there's an initial decay. That's called the slope. There's some kind of upwards growth. That's what will be the ramp. In this case, it's not a linear ramp, but an exponential ramp, as I'll discuss. And then some kind of late time plateau, which is sensitive to the finest, the smallest level spacings in the system. Okay. So that's the goal. Now, the way this works, and the way a lot of these recent analytical calculations have proceeded, is to set up a path integral representation of the spectral form factor. In the general case, you can write this G quantity as an integral over some collective variables, G and sigma. The details don't matter too much. But basically, G is the Green's function of two fermions, and sigma is a Lagrange multiplier that enforces that identity, and then sigma becomes a self-energy for the fermions. And these alpha and beta indices are replica indices that refer to the two different contours here. So you can have correlations within one contour, within the other contour, between the two contours. And because you have disorder, which is correlated between the two contours, literally identical, there are inter-contour correlations in this path integral. And analyzing this path integral is what Sod, Schenker, Stanford did for the Q equals 4 case. Here we're going to talk about the Q equals 2 case, where again, it's just free particles. And in this case, we can integrate out the Green's function G to just give a representation of the spectral form factor in terms of an integral over this collective variable sigma. And the structure is just you have fermion determinant here, where the fermion has a kinetic term dt and this self energy sigma, and then you have a sigma squared term in the action. So it's a relatively simple theory, and we're going to look for saddle points of this, and those will be sufficient to give us this behavior. So first, let's talk about the slope, the initial decay. For this purpose, let's look at the equations of motion. So you have this time derivative and you have the sigma, and then they have a matrix equation where time derivative sigma dotted into sigma is a constant. Okay. So this is a quadratic equation. It's a quadratic matrix equation, but we can solve it using the quadratic formula, basically. And you find two interesting cases. For frequencies that are bigger than 2J, you have this solution, which is the same on the two contours. So contour 1 and contour 2 have the same solution. But for frequencies less than 2J, you find that the two contours have opposite solutions. Or at least this part of it is anti-correlated, right? So you have this frequency bit, but then the square root has a sigma z here. This is sigma z in the replica space. So it has minus I on the forward contour and plus I on the backwards. And okay, you can just take this saddle point solution, you can plug it into the action and compute, and you get some formula, which involves Bessel functions. Nothing too surprising here. These Bessel functions come from the fact that the random matrix has a spectral distribution, which is a semicircle. Okay, so that's where these come from. And then the sum over K is the sum over images. The details are not super important, but you can get this early time behavior, and that will explain the initial decay here. These oscillations are precisely the oscillations of those Bessel functions. Okay. But that's sort of standard. What's more interesting is the ramp, okay? And to understand this, it turns out that if you look at this carefully, you'll discover there's a hidden SU2 symmetry which relates different frequency pairs. So the self energy at frequency plus or minus omega is invariant, or sorry, rather the equation of motion, and actually the full action is invariant if I conjugate this matrix of self energies by an arbitrary SU2 matrix, but where the transformation at plus and minus omega are locked by this equation. Okay. And then the key observation is that the symmetry is actually broken for omega less than 2J. That's because if you go back to this solution, when you have the omega greater than 2J, the sigma is proportional to identity. So no SU2 transformation does anything. But when it's proportional to sigma z, then all the SU2 transformations generated by X and Y, they change the solution. Okay. So you have not a single saddle point, but actually a whole family of saddle points, a degenerate manifold of saddle points. That manifold is just S2. It's the SU2 mod the S1, which is the Z rotation that does nothing. And we have a copy of this for each frequency pair. And so what you find actually is that because previously, say, as you imagine varying time for a frequency pair that was previously, or let's say for frequencies above 2J, the fluctuations are damped by square root of n, right? That's the overall n in the prefactor. But once the frequency goes below 2J, then you have suddenly these flat directions, this family of saddle points. And so you get an undamped, essentially, or a strong, much less damped fluctuation. And so these enhanced fluctuations give you a factor of square root of n for every direction that you can fluctuate in. There's 2 directions for each S2. And you can count the number of frequency pairs that live between 0 and 2j because it's a periodic in time with the period big T. And so you predict that there's actually an exponentially growing contribution to the ramp, which is proportional to n, that's the enhancement of fluctuations, to jt over pi. And that's actually what you see in this picture here. So there's no fitting parameters here. We just plug in the microscopic parameters. You see the slope, you see the wiggles, and you see this growth. And so the message here is that the reason why you're not getting just a linear in time growth, which would arise from a single saddle point or a single simple family of saddle points, as in Sod, Schenker, and Stanford, you have this very large degenerate manifold of saddle points. And these saddle points give you this very funny kind of exponential growth in the spectral form factor, which we call an exponential rate. In fact, you can even, by zooming in, see the discrete steps, because this is not actually jt, but the integer part of jt over pi. And this is actually visible in spectral form factor and is actually predicted by this counting of the frequencies. Okay.
This, Brian, this SU2 symmetry is mixing the 2 legs, is that right?
That's right, it's mixing the 2 legs.
Mm-hmm. Should we think of it as some kind of replica symmetry, or is it?
Yeah, it's a generalized replica symmetry where you rotate the replicas into each other.
Okay.
But it doesn't generally exist for, I mean, there's like a discrete permutation symmetry of replicas, but because this, for example, this G alpha beta to the Q is like, it's not a matrix product of G copies, it's really the individual replicas raised to the Q power and then sum for all replicas. So it doesn't have a nice symmetry structure, a continuous symmetry structure. Whereas when you square it, actually, it turns out that it does. Okay. So that's an example. Again, this is not meant to be representative of all integrable systems because the behavior there is very varied. But this is an example of what you can get and shows off some of the technology that one uses in the recent analyses. These path integral techniques, the search for interesting saddle points that connect the 2 sides. You can see that although this saddle point is diagonal, meaning it doesn't have correlation between the 2 replicas, this generalized family of saddle points where you rotate in X and Y that will correlate 2 replicas. So it's a replica correlated saddle point or set of saddle points. And these correlations between the replicas are what give you the spectral form factor, which in this case is has this interesting exponential ramp. And I'll just mention, this is, I talked about our work, but there's another paper by our colleagues, which they studied a slightly different problem, just the complex version of this. They get a slightly different coefficient here for the exponential ramp, but they also obtain this plateau, which we did not study. So now let me contrast that with the many-body chaos, strong many-body chaos. This is what you would get if you took that system that I just showed you and added some kind of scattering, multi-particle scattering to this problem. So then, as I indicated before, the expectation is you're going to get some kind of random matrix behavior. To just review briefly random matrix theory, the idea there is that you have some matrix H, which you're drawing from a probability distribution, in which the components of the matrix are distributed according to some Boltzmann-like distribution with a potential V of H. This is the sort of general class where the eigenvectors of H don't matter, only the eigenvalues matter because it's a trace. And the measure is unitarily invariant. And so then you can actually just convert to a problem where you look at the distribution of eigenvalues themselves and forget about the eigenvectors. And you get this interesting form where you have the famous level repulsion, this factor of EI minus EJ to the bold beta. That's called the Dyson index. It just has to do with the symmetry, the anti-unitary symmetries in the problem. And then this product over the potential evaluated at different eigenvalues. And this is a probability distribution. It's very complicated. You can try to analyze it in various ways, but a favored way to look at it, and the simplest way to see a trace of this level repulsion, is to look at the 2-body correlation of the energy eigenvalues. And that can be packaged in various ways. And as I said, we're going to package it in the spectral form factor, which is just the trace of the time evolution. I'm going to allow now what I call a filter function, which can zoom in on certain parts of the spectrum or do various other things. And then I'm going to average this over the random matrix disorder. And basically, because there's two factors of E, EI, EJ, this is going to be related to the 2-point function of the energy eigenvalues in this ensemble. And here again is the famous picture of what you would expect, the spectral form factor. You have the initial slope. These wiggles are again some Bessel functions, and then the ramp, which in this case is very linear. It's a log-log plot, but it's actually linear on linear plot as well. So you have this linear ramp, and then at very late time, at times of order the inverse, many by level spacing, you're going to get this plateau region. So what this talk is really about is the ramp and how the ramp emerges from this other stuff here. And for that purpose, we're going to define a time called the Thouless time. As I said, this originally came from some discussion about mesoscopic transport. It had to do with the sensitivity of transport to systems boundary conditions. But here we're just going to define it to be the time scale at which the connected part of a spectral form factor looks like a pure random matrix, spectral form factor. So just some definitions here. It's convenient to subtract off the disconnected part where we average first and then square. And this connected part is just the connected 2-point function of energies. And then this Thouless time is just going to be the time it takes for the connected parts to approach the linear in time behavior.
Sorry, is there a more quantitative definition? I mean, it seems very wiggly.
Yeah, I will make it more precise later, but basically we can ask that we're, say, within some additive epsilon of the pure random matrix ramp. Anyways, I'll give you the formula for for the entire behavior, and so however you want to quantify closeness, you can use that.
And I guess many systems have infinite Thouless time then? Like many systems do not come close to this particular random matrix ensemble?
Sure, yeah, I guess you could say it that way. Yeah, there are many examples of integrable systems which don't ever have a ramp.
Is that the only out? Are you basically saying that everything is either integrable or has a ramp?
It may be a matter of what you mean by integrable. Like, there's not much teeth in it. I can just say everything doesn't have a ramp is integrable. It's not clear that's a useful statement. But let's say that it seems to be pretty generic that if you have some reasonably generic system, you have a ramp because it's chaotic. And the exceptions are like integrable due to free particle or beta ansatz or like many-body localization. And we don't know a lot of other sort of reasonable models. At least I don't know a lot of other reasonable models that are exceptions to that point.
Okay, but in particular, there's no other sort of universality classes of generic models.
Yeah, I mean, I would say most of integrable systems are actually not stable classes. I mean, they're not stable under small deformations of the Hamiltonian. The exception is MBL. Or a notable exception is MBL, but like free particle or beta ansatz integrability typically dies once you make a perturbation. So many-body scars you may have heard about, they also typically die once you make a perturbation. So maybe there's the other interesting case that I can think of is glassy systems. And this is actually something we're working on, but very briefly, just the answer seems to be that you have sectors, and within each sector it's random matrix-like, but the sectors don't talk to each other. So you can have kind of many copies of random matrix behavior, but nothing more than that we've found so far.
And if I have a system with global symmetry, do I need to make some kind of refinement of this discussion depending on what the global symmetry is?
Yeah, so when you have a global symmetry or any kind of disconnected blocks, then you just basically count the number of blocks that you have, and that just multiplies spectral form factor. So I'll comment on that a little bit later.
Okay. Thanks.
Yep. This is just, I'm going to skip this just because it's not much point, but basically this is just how you derive this ramp from random matrix theory. I'll just point out that there's a very precise coefficient here. You're supposed to integrate over energy. You have your filter function squared. And in the regime of times we're interested in, which is times much less than the inverse many-body level spacing, this is the many-body density of states. So 1 over it is the level spacing, which is very small, like e to the minus system size. So for reasonable times, not long compared to that inverse level spacing, the ramp for GOE, say, which just means unitary ensemble, so you don't have like you have generic complex entries. The ramp is just integral over all energies, time over 2 pi, and this filter function squared. Okay. Just to comment about the filtering, one common thing you'll see in the literature is what people call thermal spectral form factor, where this filter function is just the Boltzmann factor, e to the minus beta h. That's perfectly fine. In that case, you can do an integral and you get some nice expression where E min and E max are like the edges of the chaotic region of the spectrum. So the only point I want to make is that this is not really thermal in the conventional sense that you're familiar with. Like it doesn't zoom in on a certain set of energies whose energy is determined by the inverse temperature beta. It still knows about the whole spectrum. So if we want to zoom in, we can do that using a Gaussian filter. There should be a minus sign here, but apart from that, you just filter the spectrum with this Gaussian wave packet. And then if you do that, you can zoom in on energies near this center energy E bar, and then you have a very universal prediction for the coefficient of the ramp. It's just square root of 2 pi, the variance of the Gaussian times time over pi times this Dyson index. And there's a lot of reasons why this filtering is useful, but one of them is that it can sort of smooth out features, like because over the whole many-body spectrum, you can have quite a different variety of level spacings, because the inverse level spacing at a given energy is like e to the minus entropy. So because the entropy varies, you can have many orders of magnitude variation in the Heisenberg time. So zooming in on a particular band of energies can filter out those different set of Heisenberg times to the plateau and give you a much cleaner ramp and plateau behavior. It also helps us zoom in on different regions of the spectrum to think about, really thinking about a given sort of thermal-like state where we have a certain set of fixed energies available to us. And this is a kind of already said, you can study this in various models, either with exact diagonalization, various numerical techniques, or in using some exact calculations. And the thing I want to emphasize, which I think has not been emphasized a lot before, is that the time dependence and the exact coefficient seem to be universal. So just no matter what you do, basically at long enough time, you always get this formula, say here for the Gaussian filter. So we won't, that's a very general observation. We want to understand where that generality comes from. Okay.
Sorry,
now,
didn't you just say that it comes from random matrix theory, that the coefficient is known?
Random matrix theory predicts the coefficient, but it's far from clear that you know, that every system has the exact same coefficient. I mean, like for example, if I look at this 2-point function of energies, the linear in T comes from the fact that it's 1 over E squared at large energy difference. Okay, so it's just a Fourier transform of some spectral function. I mean, some decay, some polynomial decay. But you might say, okay, fine, maybe that decay exponent is universal, but couldn't there be some renormalization out in front, like a quasi-particle renormalization, you know, in some kind of Coulomb gas analogy? It's not clear why, at least not clear to me, a priori, why the coefficient itself is perfectly.
So it's a finer test of random matrix theory.
Yeah, that's right. Okay, so now let me come to the kind of the first, the second main result, which is an analysis of what happens when you're trying to transition from the sort of system where you have many conserved sectors, like these quasi-particles you talked about before, and you want to transition to a strongly chaotic late time regime. And the model for that's going to be a Hamiltonian H, which is composed of two pieces, an H naught, which has a bunch of decoupled blocks, none of which talk to each other, but where each block is random matrix-like. And then another matrix V that we regard as small in the sense that it causes transitions between these blocks, but the transitions are slow enough so that each block can be treated really as random matrix-like on the time scale of those transitions. And as I emphasized many times now, the spectral form factor is ultimately about return amplitudes. So the idea is we can parameterize the states of the system. We can label the Hilbert space by sectors alpha and by a label I, which specifies a state within a sector. So each sector can have many states in it. I'll give you an example of these sectors later, but just think of them, for example, as like, so the system can be in one of K potential wells. And then within each well, you can have some local oscillations and different states there. And so we want to basically study how a state initially in sector alpha and of subtype I at time t is expressed in terms of the Hilbert space. And the idea is at that time t, two things can happen. It can either stay within the sector alpha or it can transition into a different sector beta. We encode those in transition probabilities, p alpha to beta. Because this is a wave function, I take the square root of that probability. And then within a given sector beta, I have some other states. These just indicate that I'm starting in alpha and I'm in sector beta and it's time t. So this is just some state in the Hilbert space of sector beta. The only assumption here that makes this not totally generic formula is that this probability p alpha to beta does not depend on I. So it doesn't depend on which state you are within that sector, it just depends on the sector. So then the return amplitude, the amplitude to come back to yourself is the amplitude to at time t have the same state you started with. And that's just going to be this return probability, the probability to go to alpha back to itself, times this overlap within the sector. Okay.
Sorry, Brian, can I ask a quick question?
Yeah, please.
These sectors, how should I think, are they arising from some symmetry, or is this just like take some Hamiltonian, you have some like nearest neighbor interaction, so it looks roughly like almost diagonal? Or...
Yeah, I specifically not specified to emphasize the generality, but yes, you could imagine, like I said, like think about a two-level system, a double well system where the particle can be in one well or the other well, except for each well is like a chaotic billiard. So you like one billiard, two billiards, and a weak link between them. So you can sort of chaotically move around in one billiard or the other billiard. And absent this weak link, you just have two decoupled blocks in a Hamiltonian. Then when you turn the link on, you can tunnel weakly between the two. And that's what this V is doing. But in a many body context, this could, for example, be different long wavelength energy modes, which have not had a chance to decay much yet. And that will label different sectors.
Thanks.
Yep. So then the key thing, we just assemble the spectral form factor as discussed. And the key thing is just this assumption that the average decouples different sectors. So when we average these within sector return probabilities or return amplitudes, the average, because the different sectors are decoupled in terms of the within sector dynamics, they're just random matrix like within each sector. Sectors should be decoupled, that's the delta alpha beta. And then if you then look at what you have, it's just spectral form factor within that sector. Okay. So the sum over all sectors and over all states within a sector reduces down to a diagonal sum over sectors of the spectral form factor within a sector. And then the weighting function is just the filter, if we have it, the filter function, and this return probability, P alpha to alpha. And so if, for example, within each sector, it was random matrix-like, as I motivated before, then this SFF of alpha is just T, just T over 2 pi times the, it's just this thing I wrote here, this formula here, independent of the label alpha. And so all we need to do is sum over return probabilities. Okay. So how do we do that? Well, this is a general formula. This is one of our main results, but we can apply it to this problem of energy diffusion to bring it back finally to the hydro motivation. Let's imagine we take a system and we just break all the symmetries except energy conservation, right? So this is kind of the, in some sense, generic case. Like if you break translation symmetry, you break all your other conserved quantities, but you just specify you have a Hamiltonian, then this is the kind of system you have, energy diffusion. Then because the long wavelength energy modes decay very slowly, they have a decay rate which is proportional to the wave vector squared. That means at a given time t, there's an extensive number of almost conserved modes, modes that have not really decayed appreciably at all. You can count that by saying, well, if you ask for the mode that's just starting to decay, that's a mode with wave vector 1 over the square root of the diffusion constant times time. That's just a mode that has decayed by 1 e-fold. And so modes with wave vector much less than that have barely decayed at all. So you can just estimate the number of almost conserved modes by counting all the wave vectors with wave vector less than, all the modes with wave vector less than kt. And then a simple count shows that it's proportional to the volume, and there's some factor of this wave vector to the power d. Okay. So in other words, you just zoom out enough so you have big blocks of your system in some units of inverse kt. Oh, my pointer went away. Inverse this diffusive wave vector. And those big blocks, the energy in that block and the energy in all the blocks adjacent to it, those are all conserved quantities, right? Approximately on this time scale. And so if then again, each sector is random matrix-like, so within a block, it's random matrix-like because the fast things have happened, then the spectral form factor reduces to summing over all of these return probabilities, which in this case I can express as like a functional integral over energy density, where I'm asking what the probability is that the energy density at time t reproduces the profile at time 0, and then integrated over all profiles at time 0. Okay. That's the probability that I return to the original state, where the sectors are labeled by energy in each thermal cell, or in each diffusive cell. So, okay, you can actually do this calculation. It's a fun little calculation to do. Here I'm using the fact that the probability distribution of energy fluctuations is Gaussian. For linear diffusion, you don't actually even need the precise form, but just for concreteness, here it is. And then it breaks down to a calculation mode by mode, and you can do the simple integrals. And you find that this return probability is just a product over momentum modes of this nice factor, 1 minus e to the decay rates times time. This you can also do in, say, the regime where the wave vector can be treated as quasi-continuous, and you get this nice form, an exponential of the system size, this diffusive factor here, and then some zeta function. Okay. And the claim is this is totally general. Once you specify the diffusion constant and the dimensionality of space, as long as linear diffusion is a good approximation to your dynamics, this is the coefficient of spectral form factor, the coefficient of the linear and t thing. And so in particular, to come back to Clay's question at the beginning, given this functional form, if you want to be close to a coefficient of 1, you can just specify how long in time you need to take. In particular, once you get to times comparable to the diffusion constant divided by system size squared, that's the size of the lowest mode here, the lowest non-zero mode, then it's no longer a good idea to approximate this as a sum when you take the log. And so at very late times, it's going to be 1 plus a sum of these decaying modes. And so in particular, if say dt over L squared is bigger than some log 1 over epsilon, then you can guarantee that the coefficient is within epsilon of their pure random matrix result. And I want to point out that this was previously obtained in a many body context, as far as I know, only in one case, in one dimension for a flow K model where you had a large on-site dimension. But actually, and there it seemed like it was some special feature arising from that model. But here I'd say it's just totally general. It just follows from diffusion and from this formula for the spectral form factor in terms of return probabilities.
So sorry, so in the flow K model you mentioned, do they have some other conserved quantity?
Good, yeah, sorry, I was not clear about that. They have a U1 on-site conservation law.
Oh, I see.
And so there they really have like charge diffusion instead of.
Yeah.
Okay, and so in the last 5 or so minutes, let me come to the final topic, which is how to put this in the context of this formal theory of fluctuating hydrodynamics. Because it's fine to think about this linear theory, and that's a good approximation in many cases, but actually even for this Floquet model, they compare their results to small on-site dimension systems where you don't necessarily expect that the linear theory is perfectly okay. And the data don't agree perfectly. I mean, they agree pretty well with this formula, but not perfectly. And they fit the diffusion constant. So it's very possible and interesting to consider the possibility that hydrodynamic interactions can modify this story. I mean, this general formula here, certainly still true, but perhaps to calculate the return probabilities, we need to include interaction effects. And to do that in a nice way, we should really ultimately make contact with this formal theory of fluctuating hydrodynamics. So let me just remind you very, very quickly. I think many people in this audience know this much better than me, but for those who don't, this closed time path formalism is really a formalism about computing partition function-like objects and their derivatives, where you start with some state rho represented by this red blob, and you can evolve with different forward and backward sum evolutions U1 and U2, but where you connect now at the endpoint of the evolution. So that's this trace here. And there are what are variously called classical or R-type correlators, which are sort of correlators that are symmetric between these two or variables that are symmetric between the two contours. And then there are quantum or noise or A-type variables that are anti-symmetric. And there's a very powerful set of rules that govern the allowed effective actions. And for simplicity, I'm going to focus on this case of energy diffusion that was recently talked about in the paper of Luca and friends. And to give you some sense of how this connects to the previous probability story, if you uncomplete the square in phi a here, what you'll find is that the phi a becomes like a Lagrange multiplier that enforces a stochastic differential equation for energy, where the term in parentheses here is the non-random or average part, which is just diffusion equation. And then you have a fluctuating part, which is the sort of stochastic force. And that fluctuating part gives rise to the variance in that Gaussian representation earlier. And so essentially what we're going to do is make a hypothesis, which is that this CTP formalism suitably modified can be applied to the spectral form factor contours. This is not trivial. The contours certainly look very similar, but the connectivity is very different. And the connectivity is important for some of the rules, for example, of the CTP formalism. But the contours are similar up to what I like to think of as like defects, which you could think of these traces as different ways of connecting up these lines at the end. And so depending on how you connect the lines up, you can implement that with different local operators, which either swap or don't swap, for example, the contours. And so you might think that up to these localized defect effects, the effective action should look similar when we integrate out the fast fields. I will note that the spectral form factor requires some sense of connectivity. And so that's where the averaging comes in, because these are really decoupled contours. So we need some kind of connectivity, some kind of averaging or something to sensibly be able to assert that there is an effective action that lives on this pair and has couplings between them. A very important point is that there's no causality now in the spectral form factor because the time is identified periodically. So correlators can wrap the circle. But in terms of like the bare hydrodynamic action, where we just integrate out the fast fields and nothing else, we would like to think or assert that the bare hydro action is still essentially the same as before because the fast fields can't effectively wrap. So we need to go to long enough time so the fast fields have decayed, but they can't effectively wrap this circle, and so they don't see the difference between the CTP contour and the SFF contour. Okay, so once we have this assertion, however, that the CTP action can be put suitably modified onto this SFF contour, then we get everything we want. In particular, if we look at very long times, longer than this Thouless time set by the diffusion constant, where all the spatial nodes have decayed, we're just left with this zero mode here, which is just the zero mode of phi a times the zero mode of epsilon, which is the energy density. And you can commit yourself that up to the usual ambiguities of regulating the measure and so forth, this reduces to saying the spectral form factor in this case is just the integral over the zero mode of phi a and the integral over the zero mode of epsilon. Well, that should just be proportional to the integral over energy. And the integral over the zero mode of phi a, well, normally in the CTP, because you connect these two contours at the end, the zero mode, that is the uniform in time mode, would just be zero because they have to agree here. But here there's no requirement that they agree. And so actually it makes sense to say that this domain of integration of the uniform zero mode of phi a is actually just the total possible time difference between the two contours, which is just time t. And so you immediately reproduce up to a coefficient, which again can be important, but actually you can get by regulating this in a nice way. You can get the spectral form factor is just time times integral over energy, just from this zero mode part of the action. And then for higher powers of the partition function, of this imaginary temperature partition function, you can actually kind of get the result that you would expect from random matrix theory by just saying, well, there's a bunch of different ways I could pair up contours to get hydrodynamic-like contours. For example, if I have GUE symmetry and k powers of z and k powers of z star, there's k factorial ways of pairing them up. And then we get a SFF for each k. And this is exactly what you would expect in random matrix theory to leading order for a GUE random matrix. So the point of the story here is that just at the level of the zero mode, actually, because of the slight difference between the CTP contours and the SFF contours, we already seemingly get the linear ramp up to a coefficient that I have not tried to convince you of. And I'll note, actually, this was discussed in the context of SYK already by Saad, Schenker, and Stanford. But here we're really emphasizing that it really just comes from the hydrodynamics of energy diffusion. Then now we can do the full path integral at this quadratic level. These are just some details here. This is the action. I wrote those before. I won't say anything in detail here, just to say that we can say, look for the eigenvalues. We can discretize the time, the total time t in units of delta t. So we have a bunch of discrete moments. We look for eigenvalues of this matrix, dt times the time derivative, which turned out to be complex numbers I omega that obey this formula. Basically, I omega plus 1 is a root of unity. And in terms of this, we can calculate then the spectral form factor because it's Gaussian, a product over momentum modes, a product over frequencies. And this product over frequencies over these discrete frequencies can be done. And you exactly reproduce the formula that I wrote from the probability analysis. So the message here is that once we make this assumption that the CTP action can be put on this SFF contour, modulo the modifications I indicated, we immediately at the quadratic level rederive the results we had for linear diffusion, and we actually get the ramp itself coming from the zero mode. Okay, so that's really exciting to me. That's nice to get what we got before, but now at the very end, I'll just flash quickly that you can start to think about interactions. And this is a story that we don't, to be honest, fully understand yet. There's a lot of subtleties here. But I'll just show you one particular thing that can happen, which is that you can get correlators on the circle by taking CTP correlators and summing them over images. This is a pretty standard trick. And what this gives rise to, for example, if I look at the AR correlator, the epsilon phi a correlator, this is the correlator for the CTP contour. When I convert it to the circle contour, you see that I need to sort over these images, and I get this denominator now, which diverges at small k. So there's new infrared divergences coming from the wrapping of the time circle. And because of this, there are novel diagrams that you couldn't have in the usual CTP formalism. So for example, this could be viewed as like an RR self energy, for those who know. And this would normally be 0 because it would just be this CTP thing evaluated at time 0, which is just 0. But here, because we're summing over images, we can get something non-zero. And so just as a demonstration, you can look for a self-consistent solution where you put a constant self-energy in this RR channel. I won't go through the details, but you can ask me later. You can solve for the self-energy in terms of some formula. It turns out it makes sense to approximate it as as the self-consistent solution can be approximated just by dropping the self-energy in the right-hand side. And so you get an expression for the self-energy here, and then you can plug that back into the calculation that we did on this slide, but with now an extra term in the action proportional to epsilon squared. And what you find is that the log of the coefficient of the linear in T ramp is modified. So previously we had, where is it? This formula here, which when generalized to d equals 1 would be 1 over square root of time. Now, when we include this particular interaction effect, we find that, well, you get time and square root of the self-energy. The self-energy itself depends on time. When you trace through all the factors, you get that this is now 1 over time to the 3/4. So in 1D at least, it looks like it's a strong modification, including just this one effect. I don't think this is the only effect, but just to give you a sense. Including this one particular diagram self-consistently, you get a significant modification of the coefficient. So the conclusion is that we're basically in a position now to think about these interaction effects in this sort of hybrid CTP SFF formalism. We know that the quadratic theory produces what we expect from linear diffusion, and now we can think about these interactions, which is an interesting new theory problem. And we can try to compare with some of the numerics that have been done, for example, this flow case system, and see if we can get a better agreement with the data. So since I'm out of time, let me just flash a conclusion. I think the key takeaway for me from this is that with some asterisks, it seems like hydrodynamics, at least this energy diffusion, really implies chaos in the spectral sense. Once you make the assumption that the CTP action can live happily on the SFF contour with the modifications I indicated, then the spatial zero mode gives us the ramp, and we can actually get the right coefficient if we regulate it in a nice way. And the non-zero modes compute the return probability. This is a useful perspective because, for example, it predicts universality. After the Thouless time, you can write down a formula. Well, you can write down a general formula for the change in the SFF as a function of deforming the Hamiltonian. And after the Thouless time, this is an expectation of an A-type variable, which is just 0 according to the CTP rules. So before the Thouless time, this can change the diffusion constant. So of course, the spectral form factor is not invariant. But after that, it just immediately predicts that the coefficient should be invariant under deformations. So it seems like spectral chaos is really robust and generic, and actually just sort of almost follows essentially from hydrodynamics, which is a very satisfying conclusion because hydrodynamics is what we kind of see in nature. And this spectral diagnosis of chaos is really something much more fine-grained, although also visible in experiment. And with that, I think I'll wrap up. So thank you for your attention. As I said, I talked about tools to compute spectral form factors in systems with slow modes. We're thinking now about symmetry breaking in glasses. It's exciting to see a lot of connections to other manifestations of chaos, like hydrodynamics, like eigenstate thermalization. And there's a lot of questions. It'd really be exciting to connect this to other effective theories of chaos. We're also curious to know whether there's a hydrodynamic theory of the plateau. And then interactions, we've taken the first steps to understand, but there's a lot more to sort out there. So with that, thanks for your attention. Sorry for going slightly over.
All right, thanks, Brian. Let's thank Brian for the very nice talk. And we can take questions.
I have a couple of questions.
Please.
Yeah, one technical and one general. Yeah, maybe the technical one is just so in this effective action, do you also, yeah, maybe you mentioned that, but you also have like powers of other fields without these, quantum fields.
Yes.
Accompanying. Yeah. So those are responsible for the IR divergences you mentioned.
Yeah. So yeah. For example, this diagram can be interpreted as essentially like epsilon. I mean, basically, like let's take this term here, this lambda prime term. If you compute the expectation value of epsilon squared, or sorry, phi a epsilon, which would normally be 0, you can get some non-zero thing now because of the time wrapping. And then this is like a term epsilon squared in the effective action. So you have these now RR terms. So I would say that the new, infrared singularities come from the wrapping of the circle, from the periodicity and the laws of causality. But the manifestation is you have all these kind of new terms in the effective action once you start integrating out hydro modes.
Yes. And then, yeah, my general question. So did people consider translation, like spatial translation invariant cases for these random matrix ramp story?
As far as I know, there's no exact calculation for those. I'm sure people have looked at small size spectral statistics, although typically they would break the translation symmetry by introducing a local like disorder field, even with perhaps a very small coefficient, but some local disorder field. So I don't think it's been looked at very carefully as far as I know. In particular, you know, I guess you're probably getting at like, could we see like full hydrodynamics, like with spatial translations and like sound modes and so forth, and how that would enter into this story. And I think that's really interesting, but it is challenging from various points of view in terms of, I mean, you could definitely do it in this formalism, but in terms of like comparing to some numerical result, it's hard because you typically have a lattice or some disorder, and it's difficult. But I think it's interesting and would be really cool to see a comparison there.
Right. Yeah, one reason, I mean, from my perspective, that might be interesting is even just there's a CTP formulas has IR divergences in that situation. So one would wonder, what happens.
Yeah, that's one of the reasons why we consider this energy diffusion case first, because it has, as you know very well, weaker sort of long time tail effects in the usual CTP context. So we're kind of more isolating this circle, this periodic in time physics. But yeah, I think it's super interesting to understand how these things fit together.
All right, Tolia has a question.
Hi, thank you for an interesting talk, and thank you for an opportunity to ask a question. I just want to understand the conclusion. Maybe I didn't get the point that hydrodynamics implies chaos in some way. There are examples of integrable models which exhibit ballistic transport, and I think also diffusive transport. And of course, there is non-chaotic systems which have anomalous transport close to MBL transition. So in what sense I should understand this conclusion? Yeah.
Good. Yeah, so the very literal sense is just what I said here, which is that if I literally imagine that the only slow mode is energy diffusion, it has this action, then I compute, as I showed you, and I get a linear in time ramp with the return probability interpretation that I showed you. Okay. So in these other cases, you know, a potential way out is that there can be a lot of other slow modes in the system. And so this energy diffusion theory is not the correct complete theory of the slow modes. And then once you have that more complete theory, you can compute and you get some other answer. Near the MBL transition, for example, but on the chaotic side, presumably at very late time, you will still see a ramp, but there can be a lot of slow modes, novel slow modes arising from proximity to the localization transition. And I don't necessarily know how to incorporate those slow modes in an effective theory that I could use to calculate, the analog of this coefficient here. So presumably if I knew how to calculate the dynamics of those slow modes, if I knew what they looked like, then I could try to calculate something like this, and it would still give me a time scale to approach the ramp at very late time.
Excuse me, are you essentially saying that in the integrable case, when we know that level statistics is not Wigner-Dyson, that in those cases when we know there is diffusion, And we know analytically from the works of Thomas Prosen that there are cases with diffusion. You're making essentially a prediction that there are even slower modes. Besides diffusive modes, there are subdiffusive modes. That's, I think, a very strong prediction to make.
No, I'm not. I don't say that they have to be subdiffusive. I say that there have to be other modes that have some other slow. Maybe diffusive is enough. I honestly have not thought very carefully about it, so let me not make a super strong claim. But yeah, I think you have to have some other slow modes. And well, let me put it this way. Just having diffusion of a quantity is not enough. It's not what I mean by hydro. I mean that literally that's the only slow thing in the system. Now, maybe the example you're giving still fits this bill somehow in a way I don't see, in which case I would definitely have to retract that assertion. But at the moment, I don't know of a counterexample where I understand, both sides of things.
Thank you.
All right, maybe let's take the last question from Edward and then move on to the discussion.
Hey, Brad, I just had a quick question for systems that have a semi-classical limit. Often the sort of one way of thinking about the universality of the sort of linear and T ramp is sort of the diagonal approximation, sort of in kind of like a Berry spirit.
Yeah.
How does that sort of tie in with this picture here? And I guess one question is, can I think of incorporating these interactions in the hydro theory as going beyond this diagonal approximation in some sense? Or?
Good. Well, I think the diagonal approximation is very much the intuition throughout, in some form, is very much the intuition for the ramp throughout all this work. So, for example, where's a good slide? So like for these flow K models, basically you can think of every step as like some kind of, it's not a random unitary, but it's a unitary with some randomness in it, and you stack them, you repeat them, right? And if when you take the expectation of two copies of these stacks, if it reduces to correlating sort of, diagonally across the circle like a ladder, then that's this diagonal approximation. All the off diagonal terms vanish, but you still have this choice of like how to orient one circle relative to the other. And that time translation is exactly this factor T.
Right.
So in the work of Prosen and friends, like it's just very explicit. You're just counting this essentially discrete time translation. And also in the Sod-Shanker-Stanford calculation, you're counting these time translations. And even in this sort of hydro formalism, you're essentially just integrating over the relative time orientation of the two contours. That's what this phi A is. Now, for the second part of your question, you mentioned, right, rather these return probabilities and so forth was going beyond, or the interactions was going beyond the diagonal approximation. I don't think so. I think what it is rather is that there's some, like, basically you have these sectors and the sectors are not totally decoupled. So maybe you could say it's going beyond. I think it's more like you have these sectors which you're still treating diagonally, but the way the sectors kind of glue up together to form a bigger random like block, that takes some time. So you have some like time scale for the subblocks to effectively glue into a bigger block. And that's what this return probability is telling you. Like initially you have a ton of blocks that are all decoupled, and then over time they glue together into bigger and bigger subblocks. But as I emphasized, the ramp doesn't care about how big of the Hilbert space. It just cares, it just has this coefficient, this independent of the like entropy. And so as you glue the little blocks to bigger blocks, the coefficient, the ramp of the bigger block is the same as the ramp of the subblocks, and you have fewer blocks. And so you get this decay to the pure random matrix behavior.
Thanks.